right, let's start looking through these. I know there were quite a few people out on Tuesday, so I want to make sure that I'm clarifying. Please ask lots of questions if there's any pieces that you are confused about. On part A, this notation down here tells me that I am approaching what x value? From the left, yes. So we are going to approach x equals 3 from the left side. So as I approach that x value from the left, my y values are getting progressively closer to what? To 1. It does not matter whether or not we ever actually arrive at that y value. We're just stating what we're getting closer and closer and closer to each time. How is the notation on part A different from the notation on part B? We are approaching it from the right. Remember, pluses and minuses up where the exponents normally belong. Tell me which direction I'm approaching it from. So we are going to approach x equals 3 from the right. And one thing I just want to make sure that I've been really, really clear on, because there tends to be a little bit of confusion about this. When I say I'm approaching it from the left, that means I start on the left side of it, and then I move towards the right, but I'm starting on the left. When I say I'm approaching from the right, I start to the right of that value, and I move backwards towards that x value. What is the output? What is the y value that I'm getting closer and closer to as I approach x equals 3 from the right? I'm approaching 0. We don't ever actually get there, but we're getting closer and closer and closer to a y value of 0 there. When I look at the notation on part C, I don't see a little plus or a little minus. What does that mean? Both sides. We are going to approach x equals 3 from both sides. As I approach from the left, you told me my y values are getting closer to 1. As I approached from the right, you told me my y values were getting closer to 0. Am I approaching the same y value from the left and the right? No. That means my limit does not exist. We've got a nice little jump discontinuity here. I was asked in first period if there was conventional shorthand for does not exist. Yes, DNE is perfectly appropriate shorthand for does not exist. I like that as well personally, but if you write DNE, that is one that is consistently used often enough that that is valid mathematical notation.
No, but like Mean Girls, like you did the breakfast now.
I actually have that meme. A, B, and C are all talking about limits. How is that different than part D?
It's evaluating.
It is evaluating. So this is saying if I had the function rule, I'm going to plug it in, see what my output is. We're going to evaluate the function. At x equals 3. So what I'd be looking for on a graph is there a filled in dot where the x value would be 3?
Yeah.
Yes. Right here, we have a filled in dot. What is the y part of that ordered pair? 1. So f of 3 is equal to 1. Sometimes a function will evaluate to something that is not the same as the left-hand and right-hand limits. A lot of times when we see holes on our graph, it has a hole for the continuous part, but then it is defined somewhere else. And we'll look at an example of that later today, because I want to make sure to point out the difference between a hole, a removable discontinuity, and a jump discontinuity. All right, there were 3 more parts to this question. Can we approach 4 from both sides? No. I can approach it from the left, but I cannot approach x equals 4 from the right. So does the limit exist as x approaches 4 from the right? Does the limit exist as x approaches 4? No. I have to be able to approach it from both the left and the right side in order for the limit to exist. If I can only approach it from one side, then the limit does not exist. Can I evaluate it at x equals 4? Yes. What does it evaluate to? 1. Last part on this graph, part G, I'm approaching x equals 1. From which direction? Both directions. Can I evaluate it there? No. It has an open circle. It has a hole. It does not evaluate at x equals 1. Does it have a limit? Does it have a y value that it's getting closer and closer to on both sides? 5. So my limit here is 5. It does not matter that we can't ever arrive at x equals 1. What matters is, am I approaching? Am I getting closer to that output from either side? All right. Example number 5. We're going to look at some end behavior and using limits to describe our end behavior. Hopefully, this concept as a whole is familiar to you from Algebra 2. The only thing that's really different is how we're going to write it. We're going to write these as limits instead of as x approaches. So over here on the right side of my graph, I would write that the limit of f of x as x approaches. How do I talk about the right-hand side? Positive infinity means I'm moving to the right forever. Visual inspection of the graph tells me that what's happening to my y values as my x's get bigger and bigger and bigger. We're approaching infinity. My y values are also getting bigger and bigger and bigger. On the left side, the limit of f of x as x approaches. How do I say I'm looking at the left? Negative infinity. My x's are getting smaller and smaller and smaller. I'm moving farther and farther to the left. Visually inspecting the graph tells me what is happening to my y values as I do that. They're going down forever. So they are approaching negative infinity. Should feel very similar to the way you wrote it in Algebra 2, except now we've introduced this limit notation. If I don't have a function rule, or if I don't have a name for my function, I'm just going to call it f of x. We never just write limit equals. It's limit of a particular function. Left-hand side of this second graph. So the limit of f of x as x approaches negative infinity, because I'm on the left-hand side of this graph, what are the y values doing here?
It's positive.
Going up, so it goes to positive infinity. And then down here, tell me how to write this limit.
You lim x, and under that would be x approaching infinity.
Yes, limit of f of x. Underneath that, x approaches infinity. What is that limit? Negative infinity, because it is going down. I want you guys to do the next two graphs on your own. I'll give you about a minute to do the limits on those. What is going on in the graph to the left? Right here.
Do you think something because it's the lowest point is negative 2?
Nope,
Okay.
because we're just describing our end behavior here. Ezekiel, I'm sorry, what did you say, dear?
I said thanks.
Okay.
Limit of f of x.
That's limit.
Of x approaches infinity equals infinity.
Yep. What about the other side?
I
It approaches positive infinity, and the limit is opposite.
Yes, absolutely. Since my ends are going the exact same direction on this one, there is something that I could do to shorten it up a little bit. So we could write the limit of f of x as x approaches positive or negative infinity. Since it has the same behavior on both ends, I can put positive and negative infinity here. That is equal to positive infinity. Both sides, both ends are going up. What about the other graph? What's happening here?
As it approaches both positive and negative infinity, the limit is
Yes. The limit of f of x as x approaches positive or negative infinity is equal to negative infinity. It's going down forever. Beautiful work. Couple more graphs for us to look at, and then we're going to spend the rest of our time on some expressions, because your homework for tomorrow is almost all expressions that we're going to evaluate the limits of. On part A, I'm approaching what? Negative 2 from the left. I'm approaching negative 2 from the left. What y value am I getting closer to? Negative 1. On part B, what value am I approaching and from which direction? Negative 2 and from the right. As I approach from the right, what y value am I getting closer and closer to? Negative 1. What direction am I approaching in part C? Both sides. Am I approaching the same value from both sides? Yes, left-hand limit was negative 1. Right-hand limit was negative 1. So the limit is negative 1. Do I ever actually arrive at negative 1? No. This is a great example of a removable discontinuity, a hole. If I were to ask you to evaluate f of negative 2, what would it evaluate to? Negative 2. This right here is my filled in dot. So that ordered pair is negative 2, negative 2. It evaluates to a very different value than where the limit is. For the limit, I'm looking at what the overall pattern is, what I'm approaching as I get closer from both sides. The fact that I never arrive there does not mean that my limit is somehow different. Does that make sense? Okay. What about the limit at negative 5? Does not exist. Why? Yes, there is a jump discontinuity here. Notice with a jump discontinuity, we not only have to pick up our pencil, but then the pattern is different on the other side. Removable discontinuity, my pattern is not different on either side. There's just this one point that's out there. Jump discontinuities, we have a completely different pattern. So does not exist. What about as we approach 5? Does this exist? What am I approaching from the left? I'm approaching 1. What am I approaching as I approach it from the right? 1. Left hand limit and right hand limit the same? Yes. So we do have a limit here. This is very similar to what we looked at with negative 2. It has a hole there, but the pattern on either side has me approaching the same y value from the left and from the right. I want you guys to try the next graph and those 5 questions there. I'm going to give you about 1.5 minutes, 2 minutes to do that. Can I approach negative 2 from the left?
Yes.
Yes. What's the limit there? Negative 2. Can I approach negative 2 from the right? What am I approaching? Negative 2. Can I approach it from both sides? Yes. Left hand limit equals the right hand limit, so my limit at negative 2 is negative 2. Does the limit as x approaches -4 exist? Limit does not exist. We have a jump discontinuity here. So it does not exist. What about the limit at 5? -0.25. I can approach it from the left. I can approach it from the right. I'm trying to figure out what y value I'm approaching. Looks like it's about 0.25. Or sorry, -0.25. Or you could write that as -1/4. For any values like this where it's not at a whole number, you're just kind of having to approximate or guess. If you say -0.25 and I'm like, well, I don't know, that looks like -0.3 to me, we're going to call that even. I'm not going to get picky about those decimal values from a graph. All right. Places where I will get picky, though, is if we're using a function rule to evaluate. So let's look at the last several examples that you have. We talked on Tuesday, easiest way to find a limit is to do what? Substitute in. Easiest way to find a limit. We're going to sub in. So let's do that on part A. I'm going to have 2 cubed minus 8 over 2 minus 2. What happens? I get 0 over 0. I talked on Tuesday about how this is a very special situation. When you see 0 over 0, what does that mean?
A whole.
This is a whole. Yes. So we're going to factor, we're going to cancel out that whole, and then we're going to sub in again. Look at this numerator. Does it factor? Yes. This is one of those situations where I use SOAP to help me factor. I'm so happy that you guys love it so much. All right, so remember, if I have a sum or a difference of cubes, I need the cubed root of each of those pieces, and then I'm going to have a linear factor that has the same sign. And I will have a quadratic factor that has the opposite sign and then always positive. All right, so help me factor that numerator. Let me write down my denominator first. It's all over x minus 2. How will my numerator factor?
X minus 2, x squared, plus 2x.
Yes, x minus 2, and then x squared plus 2x plus 4. When you get it in its factored form, what do you notice? X minus 2 is canceled. That's what is causing the hole there. So I'm going to take this right here and we're going to sub in again. So then I would have 2 squared plus 2 times 2 plus 4. So I've got 2 squared, that's 4. 2 times 2 is 4, so 4 plus 4 plus 4? 12. There's my limit. So we factored using a difference of cubes. Once we've canceled out our whole, then we can substitute in again. So graphically, this is like that one where we see our fingers are running together from the left and to the right, approaching the same y value, but it's not defined right at that value. I want you guys to do number 2. Substitute in first. If you get a 0 over 0 situation, then you have to factor and cancel. If it comes out as a fraction, please make sure you fully reduce any fractions that you find.
Do we have to factor the denominator?
Only if you find you're in a 0 over 0 situation.
So if we just get a normal number, then that's it.
Then you're done. Yep. What'd you guys get for the limit here?
5 over 2.
I got something close to that, but I didn't get 5 over 2. I got 5 over 4. All right, so let's walk through it.
Oh, I see.
Yep. All right, so I'm going to substitute 4 in the place of x. So I've got 4 squared plus 4 times 4 minus 12. So up in that numerator, I have 16 plus 16 minus 12. 16 plus 16 is 32. 32 minus 12? 20. So I get 20 up in the numerator. Down in the denominator, I have 4 squared minus 2 times 4 plus 8. So 16 minus 8 plus 8, I get 16. And then I can divide both top and bottom by 4 to reduce it. So we get 5/4. We always substitute in first before you go through the process of trying to factor and cancel. It might not be necessary to factor and cancel. You only need to factor and cancel if you get a 0 over 0 situation.
What if you're in the 0 over 0 situation? You don't have to fix it.
Huh?
What if you're getting a 0 over 0 question? You just don't know how to fix it.
Then we can talk about it. But it does mean that there is a hole, so the limit does exist. Yeah, we'll talk about that one in a minute. Let's look at number 3.
0.
We get a 0 over 0 because I'm going to have the square root of 9 minus 3, so that's 0, over 9 minus 9, which is also 0, so this has a hole. Does the denominator factor?
No.
No, it's a linear factor. However, what do you notice about that numerator? What does it have in it? Has a square root. I'm going to treat this denominator like a difference of 2 squares situation. If I treat it like a difference of 2 squares, let's just pretend for a minute that instead of x minus 9, it was x squared minus 9. How would it factor then? X minus 3, x plus 3. Since it's not x squared, I'm still going to take the square root of it, so I would have the square root of x minus 3 and the square root of x plus 3. If I use the distributive property here, would I get my original denominator back? Square root of x times the square root of x would give me x. Square root of x times 3, negative 3 times square root of x, that middle term is going to cancel out because of the positive and negative. Negative 3 times positive 3 gives me negative 9. We won't need to because we're going to substitute in. Yeah. I do see that this will cancel though, which leaves me what in my numerator? 1 over the square root of x plus 3. And now I can substitute in again. So I would have 1 over the square root of 9 plus 3, which would be what? 1/6. There's my limit. That denominator, when I look at it in relationship with the numerator, this is one of those quadratic type equations. It's not a quadratic, but I'm going to factor it like it is a quadratic. Number 4. Ugh.
Why do you do this to us?
Because I love you guys very much.
Sure.
I also want to make sure that you're well prepared for what comes after this. It's one of the least caring things I could do is to not prepare you well. What are we substituting in for x? 0. So I have a 0 in my denominator. I already know that it's undefined here. What I don't know is whether that means the limit does not exist, because it's an infinite discontinuity, or if it's a whole. If I get 0 over 0, it's a whole. So up in the numerator, I have 1 over 0 plus 5 minus 1 over 5. What happens in my numerator? I get 0 over 0. It's a whole. All right. Is factoring the way to go on this? Probably not.
I don't want that activist.
What I could do up in this numerator, though, is instead of having two fractions that are being subtracted, I can get myself a common denominator and write it as a single fraction up there. So I'm going to multiply this first fraction top and bottom by 5. And the second fraction, I'm going to multiply top and bottom by x plus 5. So I'm going to rewrite what I just did there. So I have 5 times 1 minus 1 times x plus 5 over my common denominator that is now 5 times x plus 5 all over x. Ugh. 5 times 1 is what? 5. So that's just 5. What do I still need to do to this, though? I need to distribute this negative 1. So I'm going to have 5 minus x minus 5 over 5 times x plus 5 I'm going to just write divided by x instead of continuing to have that big old fraction there. What happens in this numerator? Yeah, the 5s cancel, and I have negative x up in my numerator. So I've got negative x over 5 times x plus 5. If I am dividing something by x, that is the same as times 1 over x. I'm multiplying by the reciprocal. What's going to happen? My x's cancel. There's my whole right there. So I have negative 1 over 5x plus 25. Can I substitute into that? Yes. What am I putting in the place of the x? 0. So I have negative 1 over 5 times 0 plus 25. What's that going to give me? Negative 1 over 25. There's my limit. All right. Looking at our time, I am going to skip number 5. If you guys want to know how to do this, this would be a multiply by the conjugate situation. It's not on your homework, so we're going to skip it for right now because of time.
Yeah, it's not on the test.
No, it's not on the test. I do want you guys to try number 6 on your own, though. Try number 6. We're going to skip this one for today.
Great. I got 91. I got 91 on that Euro test. You get like.
I'm cheating. Actually, no, I'm not cheating, please. I got 100.
Which is wrong with you? We get it, you're a one-upper. We get it, you go home and immediately do your home. France.
I see. That's what
I didn't care enough about English.
Try to finish up number 6 in the next minute. Where are we able to find the limit on number 6?
5.
5. Factor the numerator. There is a factor that cancels, and then you substitute in. Couple quick notes, just so you guys kind of keep this in the back of your mind. If you get 0 over a number when you substitute in, the limit does exist. It's 0. If you get a number over 0, that is an undefined situation. The limit does not exist. 0 over 0 means there's a hole and you've got to do a little bit more work. The limit will exist. You just have to get rid of that hole. Number 5, this is a situation where you would multiply by the conjugate. If you're very interested in seeing how to do that, I will post my work for that. Homework is due tomorrow. We're going to start on 4.1 before the break, and we'll finish it up after the break with a healthy dose of review in there. Have a great one, guys.